a little bit about a method for approximating the value of a function, and this is going to be called Euler's method. So just a general question here to kind of begin this process. If a function is known to have a value of negative 1 comma 0, how can we figure out the function's value at x equals 1? So the function or the differential equation that I've given here is dy dx equals x squared minus y squared. Now, here's the issue. Traditionally, if we want to find the function's value of 1, well, we have to find what the function actually is. And if we're given a differential, we would want to separate variables and be able to take the integral of both sides, finding the function, and then we simply plug 1 in. One little problem here. This differential equation right here, x squared minus y squared, you are not able to separate the variables. And so in this circumstance, we're going to be left with a little bit of a problem. We're not going to be able to find the original equation. And so not all functions are going to ever be integrable. However, we may still need to find values of the functions that have a known differential equation. So Euler studied a numerical method of how we're going to accomplish this, and we're going to call this Euler's method. Now, one thing I have some links just above this video for you to check out is why would you want to numerically approximate a function? So a movie, I believe that came out either, I would say last year, which would be 2017 or 2016, called Hidden Figures, actually talks about Euler's method and actually was used to help John Glenn come back from space when they were trying to track out trajectories of where the spacecraft would land. So check out these different clips, articles, and reports that I'll have linked on Canvas right above this video. But we're going to go ahead and talk about how we would actually let this work. So remember that we have a known value of the function, negative 1 comma 0. And so what we want to do is basically look, this is the slope field for x squared minus y squared. So I can kind of follow the slope field, kind of, sort of, get an idea that 1, it's going to be somewhere right there where my cursor is circling, but I'm not exactly sure. So what we're going to do is we're going to look at the differential equation because I can plug negative 1 in for x, and I can plug 0 in for y. And when I do that, I'm going to get a dy dx of 1. So what that tells me is that the slope field at this value right here is going to be 1. Well, I could follow that 1 as far as I want, and that's going to give me an approximation. If I go really short distance away from that red point, it's going to be a pretty good approximation of where the function would be. If I go really far away, as my mouse just went, not going to be a good approximation. Well, how well you want to make that approximation is completely up to you, or in the case of the question, whatever they'll provide to you as that distance. So we're going to let our delta x, or a change in x, be 5. So what does that exactly mean? Well, here's what I've done. So I found negative 1 comma 0. I plugged into dy dx, and I get 1. I'm going to claim that I want to go as a delta x of 5. So that's going to be my steps, essentially. I'm going to go in steps of 1/2 x. So I'm going to go 4 iterations of this to try to figure out where this is going to go. So the change in x is 0.5. Therefore, the change in y would also be 0.5. Now, I have a little note down here. We know that dy dx is essentially approximated by the change in y over the change in x. I just multiply both sides by delta x, giving me this little mini equation that we're going to work with here. So what I've actually done is I followed that change in y and the change in x. So I essentially went up 1/2 and over 1/2. And what I've done is I've created a new point, negative 0.5 comma 0.5. That's the approximate value that I found using Euler's method for x equals negative 0.5. But I want to get all the way to x equals 1. And so we're going to repeat this process 2 more times, actually 3 more times in total. So now I'm going to plug negative 0.5 and positive 0.5 into my differential equation. What do I get this time? Well, I get 0 actually. As my delta x is going to remain 0.5, again, that will be told to you in a problem, or if you're doing this on your own, the smaller the delta x value you choose, the more accurate this Euler's method is going to be. The delta y here then, or the change in y, is going to be 0, so that means my new point at 0 is 0 comma 0.5. Now I'm going to plug 0 and 0.5 in. I get a slope of negative 1/4. My delta x is still 0.5. Therefore, I multiply these two together, just going back to this relationship down here, and I get negative 0.125. I'm almost there. I now have an approximate value for what the function is at x equals 0.5. By going one more iteration of this, finding my dy dx is 0.39. Again, my delta x is 0.5. I'm going to get 0.195 as my change in y. And once again, what I'm doing to get these values is I'm adding the change in x and the change of y to my original point. So like back here at negative 1, 0, just to kind of point out. I add 0.5 to this and I got negative 0.5. I add 0.5 to the 0 and I get 0.5 again. Or I'm sorry, not again. It's going to be a positive value for that. And we go on, we do the same thing. We add the delta x and the delta y to get our new point each time. And so what I've done is by using Euler's method is I have approximated using this differential equation that my value for this function that we cannot integrate when x is equal to 1, y should be approximately 0.57. It's really important to note that this is just an approximation. So you can see this blue curve, for example, would be the actual curve. Using Euler's method, because we're using small segments of straight lines, whereas approximations for the curves, as you can see, this green approximation using Euler's method doesn't exactly get me to the function, but it gives me a ballpark idea. So here's a little applet, and I have this also linked on Canvas if you want to play around with it. So I'm going to choose the differential equation y squared minus 2y plus 1. And so I'm going to give as an example. If I use slope field, or I'm sorry, Euler's step of point, or not point, of just 1, right? Here's would be what it would look like. Okay? So as you can see, it's not going to be exactly the best value here. Watch if I use 0.5 now. All of a sudden, it has a little more of a refined value to it. If I do 0.25, again, think of how many more calculations I'm doing here. Okay, if I'm trying to approximate the x equals 4 right here, originally I had to do 4 approximations. Here I have to do 8. Here I have to do 16. If I actually have to go 0.125, a really good idea now of what my function is actually going to be doing here by using Euler's method. All of these blue little slopes essentially are giving me a good idea. Now if I clear this out, I'm going to show you the actual. That's what the actual curve is going to be here for this differential equation. So as you can see, the bigger step of delta x we used, this is again using a step of 1 versus 0.125, look how much more accurate you get by using the smaller values of delta x. That'll conclude the introductory video on Euler's method. Please take a look at a couple of videos down below which will detail some specific examples on how you can use Euler's method yourself.